Dear students, in this video we see 1-1 and onto linear transformation. Let us first start with 1-1 linear transformation. A transformation T from V to W is said to be 1-1 or injective if distinct elements of V are transformed into distinct elements of W. That is, if U not equal to V implies T of U not equal to T of V, then T is said to be a 1-1 linear transformation or injective. Now we see onto linear transformation. A transformation T from V to W is said to be onto or surjective if for any W belongs to W, there exists V belongs to V such that T of V equal to W. In other words, if range of T is the entire codomain W, then T is onto. Now a linear transformation which is both 1-1 and onto is called as bijective linear transformation, and a bijective linear transformation is called as an isomorphism. Now in the next theorem we prove that a linear transformation T from V to W is injective if and only if kernel of T is singleton zero vector of V. Let us see the proof. First, we assume that a linear transformation T from V to W is injective, and we prove that kernel of T is singleton zero vector of V. Now let us take U belongs to kernel of T. Now this implies T of U equal to zero vector in W, which is same as T of zero vector in V. This implies T of U equal to T of 0 in V. This implies U equal to 0 vector in V since T is injective. And this implies kernel of T equal to singleton 0 in V. Now we assume that a linear transformation T, for a linear transformation T from V to W, kernel of T equal to singleton 0 in V. Now we prove that T is injective. Now for U and V in V, suppose T of U equal to T of V. This implies T of U minus T of V equal to 0 vector in W. This implies T of U minus V is equal to 0 vector in W. This implies U minus V belongs to kernel of T. This implies U minus V is a 0 vector in V since in kernel we have singleton 0 vector of V. This implies U equal to V, and therefore we get T of U equal to T of V implies U equal to V, and therefore T from V to W is injective. Now we note that if T from Rn to Rm is a multiplication by M cross N matrix A, then the kernel of T is the null space of A, and hence nullity of T, which is nothing but dimension of kernel of T, is nullity of A. Similarly, the range of T is the column space of A, and hence rank of T, which is nothing but dimension of range of T, is rank of A.